All right. Thank you. And before I start, I'd like to just say that I'm very grateful to Tacen for hosting Urbit here this week. This has been an incredible conference for me, and I think for a lot of other people. So let's all give a round of applause to Jay. Thank you very much. So my name is Ted Blackman, also known as rovyns-ricfer, and I'm the CTO of the Urbit Foundation. And I've been working on Urbit not as long as a few people, but for about 6 years now in various capacities. And so I'd like to think I've learned a few things about how to build Urbit. And I'm going to talk today about what I've learned, what kind of principles you can use, or what kind of principles we can use, at least, to try to make our own software timeless. Maybe some of that is interesting for other people here as well. And I'll talk about our core development roadmap. So where we are, where we're going, very rough timelines on some of these things. All right, let's get into it. How to get to Kelvin Zero. So there's a long quote about how to do this. I'll read it. The dream of absolute zero is an operating system whose core components are so simple, so boring, and so mechanically straightforward that we can imagine them becoming finished and never changing. We need to freeze not just a format or a protocol, but a language, a kernel, and a standard library. To succeed, we need to flush out each quirk, complexity, and creeping feature until the system is so boring and obvious that no one even wants to change it. As you may be aware, not all of Urbit has met this criteria. In fact, there are some, so there are some parts of it that have, or close to it. I'll go through these. I actually like, people usually talk about the lowest layer of Urbit as being knock, or machine code, but I like to think of the lowest layer as actually nouns. That's the data structure that everything in Urbit is built out of, right? So it's a natural number, right? Either 0, 1, 2, 3, or bigger, or it's a pair of nouns that we call a cell. So it's either an atom or a cell, so it forms a tree where the bottom of the tree is all numbers that can be arbitrarily big. Everything in Urbit is built out of this data structure, including knock, or machine code. So we don't have a Kelvin version on nouns, but we're not going to change them. Next layer up, and we usually talk about this as the lowest layer of the system, is knock. Knock is at Kelvin number 4, so we could change it 4 more times if we wanted to. My personal guess is that there's about a 50-50 chance that we'll ever get to knock 3. The chance that we get to knock 2 is very low. We don't have any plans for knock 3. Knock seems fine. That's my take. I think there's pretty broad agreement on that among the core devs. We have a lot of problems, but knock ain't one. The next one here is Arvo as being close. I skipped Hoon. So Hoon is their programming language. And actually, I skipped it on this list because there are a bunch of things that I'd like to change about Hoon. There are things that are not good about Hoon. There are problems. There are improvements that we want to make, quite a number of them. But Hoon is serviceable, actually, right? Like whenever I think about what's blocking us being able to do something in core or even in user space, the Hoon language is rarely the thing that's the blocker. So it has warts, it has problems, but you can work around those problems in just about all the cases that we've encountered, at least for its stated purpose as a systems programming language. Right? So it's statically typed, it's concrete, it's low level. It kind of feels like writing C, but it does what it's supposed to do pretty decently. So Hoon is close. It's close to being close to freezable. Arvo, the kernel proper, is actually quite close to being frozen. So when we talk about the Urbit operating system, Arvo can mean 2 different things. It can either mean all of kernel space, right? So like all of the whole operating system, including the kernel proper and the kernel modules, but it's also the name, somewhat confusingly, of the kernel proper, right? So the structure of Arvo is that it has something vaguely akin to a microkernel, and that it runs a number of kernel modules. called vanes. And those vanes mostly need a lot of work. But the kernel proper itself is actually quite close to being frozen, in my opinion. There's one big change that we want to make. That's a proposal by Philip for breadth first move ordering, when we're also going to pin the scry handler. If you don't know what that means, don't worry about it. So there's one change. It's a fairly small code change, fairly large conceptual change. But the rest of Arvo, I wouldn't change anything, really. So that's actually a pretty decent place to be, right? Like, of all the things that Urbit's trying to do, our machine code and our kernel are pretty close to where we want to be, where we want them to be. So that's a nice base to build on. So you can see the history of Urbit here, where Nock was developed first, Hoon was developed on top of that, Arvo was developed on top of that, the vanes are developed on top of that, and then user space, right? And so the oldest parts of the system have had more time to get all the kinks worked out, and they're a bit more stable. So it's not really surprising, but you do see it when you kind of think about this. There are also, I've listed 3 vanes here, Dill, Ford, and JL. Well, Ford used to be a vane, but 3 kernel space modules that I think are close to being Kelvin versioned, or Kelvin versionable, meaning close to being freezable, really. The first is Dill, so that deals with terminal input and output. So command line, you're typing in to a terminal and you're seeing text come out on the screen. Dill handles that inside of Herbert, and I think Dill is really close. Now, if you ask Palfun, who wrote the last version of Dill, there's all kinds of stuff that he wants to do to it. But honestly, I think it's fine. The same sort of happened. The same applies to Ford, I think, where like I wrote the last version of Ford, mostly, and I think there's a lot that I'd like to do with it, but honestly, it's fine. So if gun to our head, we have to freeze Dill and Ford, okay, not that bad. Similarly, jail. So jail is the module in Urbit. It's a kernel module. It's a vane, and it handles the PKI management. So I have a key, public-private key pair associated with my Urbit address. You also have one. In order for me to send a message to you, I need to know what your key is, right? And so we look that up from the blockchain. We have an Ethereum layer 1, layer 2. That filters through some applications. There are bugs actually in those applications that are a little frightening sometimes, but we can generally recover from them at the moment. But some known issues there. But jail itself, after it hears some information that's been filtered by those apps, I think is actually in a very kind of freezable, timeless state, because its conception of the public key infrastructure is that it doesn't have anything to do with Ethereum, right? It's just, hey, there's some source of public key information, and there are some things that that has to have Byzantine fault-tolerant consensus. But no matter what that is, that could be some other blockchain. If somebody builds something else that's not a blockchain but somehow better than a blockchain that still implements BFT, then jail would still work with that. We would switch to a different app, different pipeline for getting the data. And that's actually a really good sign, right? That jail itself wouldn't have to change in that situation. So that's one of the ways we know that jail is pretty close to timeless. Now, the actual code itself, we could probably quibble. I don't know if I would, love for that actual code to be what lasts for thousands of years, but it's serviceable, right? These things are serviceable. That's what I'm getting at. So these are the parts of the system that they're not bad. You're like, all right, we can work with this. Then there's the other parts of the system. These do not spark joy. This is not a complete list. Yeah, I'm not going to read them. Suffice to say, we have a fair amount of work to do. But we have learned a number of things from getting even those parts of the system that aren't done yet, things like clay and gall that have warts in them that are major warts that we need to fix. Even for those things, we've learned a lot about, believe it or not, a lot of them are a lot better than they used to be. I think Philip probably knows that more than anybody. How long have you been working on Urbit now?
It's very close to 10
Would you agree that some of these things are better than they used to be? Okay. So here's some principles that I kind of cobbled together here. So when I think about taking any module within Urbit or Urbit itself, or a subsystem within Urbit or protocol, some piece of it, and thinking, okay, how can we make this timeless? These are some of the ways I think about that. So I will go through these one by one. The first one is what we call solid state. Right, so this goes back to the beginnings of Urbit. The idea is Nock is a solid state interpreter. So this is an analogy to hardware, where in contrast to a hard disk drive that has a spinning disk and a head that moves back and forth, a solid state drive has no moving parts. So this is why you can drop your laptop and it's okay. 15 years ago, if you dropped your laptop, it was not okay because the hard drive would bust. So that's an analogy, right? But solid-state electronics have major advantages. No moving parts means harder to break, last longer, etc. So what does that mean in software? What does it mean to have no moving parts? Well, and it means a few things. It's a little vague, but you feel it when you're working on Urbit. Urbit is more solid-state than the vast majority of systems, and we're trying to build a solid-state world for software. Solid-state interpreter with Nock, where the interpreter itself is stateless, right? It just takes in a Nock expression and runs it. And then the system gives it another Nock expression and it runs that. And the way it does that is deterministic, pure functional, right? So there are no hidden inputs. There's no kind of there are no little weird dongly bits that are hovering around that affect the computation, right? And much of software is plagued by weird dongly bits. So this is a little vague, but this is probably the number one thing to think about when thinking about, can we Kelvin version this? Can we freeze it? Is it timeless? Is it solid state? And we're trying to extend this notion up into user space with solid state subscriptions. What makes those solid state is that they're backed by Urbit's immutable Scry namespace. So the data, meaning the inputs to any calculation, those all have immutable names, and they have provenance, right? But it's a solid foundation. You're having code that operates on a solid foundation, and that's a form of being solid state. The second principle is rage-driven development. If you look at a piece of code in Urbit, and it makes you very angry, you probably need to fix it. Now, this depends on who you are. If you're just someone on Hacker News, I don't want to hear about it. But if you've spent some time looking at the system, right, and you know kind of why it is the way it is, how it got that way, what problems it's solving, how much worse it could be, and you still have that feeling, that's a good signal, right? This is a way of reading from your intuition and saying, okay, this is bothering me for a reason. I don't know, maybe it's just that I'm getting old. All I can do now is my intuition. And the third, which is similar, is Grug. So Grug is a sort of hypothetical caveman. And he's not maybe very sophisticated in our modern ways, but he knows what's important. Right? So Grug say, Grug wants solid-state subscriptions. Grug want put movie into Urbit. So when you're thinking about this, like, how does Grug feel about it? We need to please Grug. It's very important, right? This actually goes back to the first quote, right? Like, it has to be simple and obvious, right? And it can be challenging, actually, to keep Grug in mind. We have to, things can get sort of heady sometimes. So this is a good check. All right, now we'll get into some more technical ones. One of the big things we've learned is to remove asynchronicity whenever possible. So, and this is asynchronicity defined pretty broadly here. It can mean a number of different things. But what I mean by it is that, let's say I'm a piece of code I'm running, right? I'm running some instructions one after the other, and then I have to stop and emit a request to some other module, some other machine, something else. And then I have to sit around and wait for some response to come back. And then when the response comes back, then I'll pick up again. All right, so this can show up between two different modules if they have to communicate. Right? I run for a little while, and then I stop, and something else runs, and then I run again. Right? Now, over the network, this is irreducible. Right? This always happens over the network. You can't get rid of that. You can't always get rid of asynchronicity. However, there are a lot of places where you can get rid of asynchronicity, and it's important to do this. So earlier designs for Urbit sort of assumed, I think Philip made this point a couple of years ago, that like earlier designs for Urbit assumed that asynchronicity would just be fine. You just deal with it. All right, just get good. You know, don't mess it up. And at some level, maybe this is true, but in practice, better not to. And so I would say that I'll give an example of this, right? So until 2020, there was a separate vein for Ford, right? So Ford was its own kernel module. Ford is a build system. It's a linker and build system. So you can give it a folder full of Hoon files, Hoon source files. It will figure out it has a little language for build directives. It'll cobble together the programs and make one program out of all those files. Right? So this is how Urbit will build an application that Gall will then run. Gall is the other kernel module that runs applications. So we're loading files from Clay, which is Urbit's file system vein. So for to load the files from Clay, do a bunch of builds. That would often have to go back and forth into Clay, and then send the result to Gall. And there's this whole triangle of communication. And the thing is that because all these things were bouncing back and forth, Ford could never really complete anything. Right? It would run part of a build, and then it'd have to go ask Clay for the next, to load the file to grab the next step of that. And this asynchronicity made it so that until 2020, we were never actually really able to perform a reliable over-the-air update in Herbert. It was just too hard. It's technically possible to get this right. Right? It's not like a mathematical impossibility to say, okay, well, you keep asking until you get all the files, and then you do what you need to do. Right? Like, it doesn't sound like it should be that hard. But it was. And asynchronicity actually really is hard. So in 2020, I think it was Joe's idea, we moved Ford into Clay. And so now Ford is just a function. Clay, the file system, as it's running, if somebody asks it to run a build, right, or if it knows it's supposed to run a build as part of doing something else it does, then it just calls the function, gets the result, keeps going. And since then, we've been able to push out over-the-air updates. I mean, we broke it a little bit the next year, but then we've since fixed it again. But since then, the number of bugs that we've had in Ford and in that whole system have been much fewer than before, and the amount of code was reduced by roughly a factor of 10. So yeah, remove asynchronicity if you can. Something similar is to remove unneeded state. And this goes back to the dongly bits. Often you just have some kind of state sitting around, right? Any computation that's stateful. Maybe it doesn't need to be stateful, right? And so a good example is from Ames, our networking vein, where when I had first written a version of it in 2019, then it had a packet queue, and separately it had a little number saying how long is the packet queue, how many packets are in the queue. So that whenever we need to know how many packets are in the queue, you didn't have to traverse the whole packet queue, right? Because that's a linear traversal. You don't do linear traversals, they're slow. So okay, just cache the number, right? Don't have to run that every time. And then whenever you add a packet, add 1 to the number. And whenever you remove a packet, subtract 1 from the number, right? Just normal, right? It got desynchronized. Like, it just did. Like, modifying the packet queue, sometimes I'd forget to add 1 to the number. Sometimes forget to subtract 1 from the number. And after a while, some ships ran into really bad problems from this. So what did we do? Well, we got rid of the number, fixed the bug. Did it make things slower? Not appreciably. Nobody cared. This is often the case, right? Often as you program, you think, oh, okay, I'll add a little cache here, right? I'll add this, there's some derived data, like, oh, I don't want to have to derive it again, I'll store it. Resist the impulse. It depends what you're doing. Sometimes you really do need that, for performance. But that should be a conscious decision. That shouldn't just be sort of a knee-jerk thing. Now, there's lots of state that you cannot get rid of. And so for that, you have the next one. Make the state explicit. This is something we've been learning really over the last year. State can be implicit in a number of ways, but one of the big ways it can be implicit is if it's in pending input and output. So let's say I try to send a packet to J. And then I just forget about it. I don't store the fact that I'm waiting for a response from him. Right? I'm sending him a message, I want to get an acknowledgement. Right? But I could just send him the message, and then maybe I don't need to explicitly track. Maybe I don't technically need to explicitly track the fact that I've sent him a message. And then there's something that happens when I get the ACK, then that triggers me to do something. Right? But now what we have is implicit state. Right? So I don't have, because I could say, oh, I removed the unneeded state from my system. Isn't that great? But I've only removed the state from my system, and if you zoom out to include the system of both urbits and the wire in between them, that state is still there, but it's no longer explicit. Now only the wire between us knows that that's there. And so then if that goes wrong, something happens in the future, I do a state migration, I change the logic in my program a little bit, I have no way of knowing whether I was in the middle of that or not. Right? So if the state were explicit and I just said, okay, I'm going to send a message to J, and I'm also going to write that down in my program. There's going to be a field. I have a message that I sent to J. Then if I upgrade, then I can look at that, right? Or something else happens later, I can look at it later and say, okay, I'm in the middle of this. So we're in the process of applying this observation in a number of ways. Philip talked about this quite a bit in his talk. So the next one is use level triggering, not edge triggering. This is another analogy from hardware. I guess we're kind of hardware wannabes here. In hardware, there are two ways of sort of reacting to a change, or reacting to something in the circuit changing. You can react to an edge, which is where it looks like an edge in a graph, right? So if you're looking at the value in a wire over time, it's either 0 or 1, right? There's either no current flowing or there's current flowing. You can look for a transition, right? You can look for that step function, the edge of where it changes from 0 to 1, and you can react to that change. Right? Or, so that's edge triggering, because you're reacting to the edge. The edge is triggering some behavior. Or you can do level triggering, where you just react if it's 1, right? So you read, like, what's the state of this? And if it's 1, then you do something. Right? And if you read it again and it's still 1, then you do it. And you read it again and it's 0, then you don't do it. And it's 1, then you do it. Right? But you're not listening for transitions. Right? You're reacting to the state, not to a change in state. So it's often tempting to write something where you're listening to the transition. Sometimes that's more computationally efficient, not always. But when you're trying to make something timeless, it's much better generally to do level triggering. And what that means in software is that you have something that's a state function, is a technical term, right? It's like basically you decide what to do based on looking only at your current state. You have no dependency on what happened before. You don't care how you got there. It's not hysteretic, right? You just care about what the current state is. And the nice thing about this is that it forces you to write your program in such a way that whatever operation you do there is idempotent, right? Meaning that if you do it twice, the result only changes once, right? If idempotent means it's like 1 power, right? Has the power of doing it once. Doing it twice has the power of doing it once, right? So, because if you have to just be able to read from that wire whenever, right? And whenever it's 1, then you do the action. Then you may do the action multiple times. And if you build all of your systems so that they're idempotent at all the different layers, you're going to have a much better time. This observation of level triggering versus edge triggering arguably is why Kubernetes is so successful, right? Because instead of listening for like, oh, we're gonna, did somebody run this command? Did one of the 1,000 machines in this data center run this command or not? Right? Or like when it runs the command, you take some action. Instead of that, there's a configuration server that says, here's what all these machines, here's the configuration that all these machines are supposed to be in. Each of those machines reads from that configuration server and says, am I in that state? No? Okay, I'm gonna take some action to get myself into that state. And then they do it again. Am I in that state? Yes. Okay, cool, I'm not gonna do anything. Right? Idempotent. Right? So that kind of idempotence, like, that's related to it being declarative, right? So you can have a declarative system where you're saying, based on this state, irrespective of how it got into that state, then we're going to make the rest of the system, sort of, as Philip would say, true itself up to what it needs to be for that state. Another one is to reclaim resources predictably, which implies that, first of all, that you can reclaim resources at all. Which a lot of parts of Herbert couldn't do in their initial instantiations. And unfortunately, when we had to go back and bolt on some resource reclamation in different places, sometimes that made the system pretty ugly. I'd say that especially in AIMS. The way we close AIMS flows, which are sort of like sockets, is we had a lot of bugs with that, and it's a little messy. And we did have to close them. But if we designed the system from the beginning to have clear life cycle semantics about flows, then I think we wouldn't have gotten into that position in the first place, right? So when you're designing the system, make sure it can clean up after itself. Make sure that any resources that it takes a lease on, that it can relinquish those resources. And we think of this in terms of system software, that's operating systems and other things that are running other code. But if you have a sufficiently mission critical application, then this is also true. Okay, this one's sort of interesting. Locate responsibility properly. This is subtle, and I feel like I haven't heard people talk about this, but I don't know why. So because I think this is very important, actually. So basically, it's important to figure out which piece of code and which user should be responsible for what. Right? So for example, we had a problem for, I don't know, 5 or 10 years, until very recently, where if I were just a ship running and you send me a poke, you send a command to some app that's running on my ship. I'm not running that app yet. Then you send me that command, and my GAL that runs my apps will just enqueue the command. And if you send me a second command, I'll enqueue that one. And if you send me a third command, I'll enqueue that one. And you can actually just keep doing this. And if I never start the app, you'll just fill up my ship. You'll fill up my whole machine. And then my urbit will fall over and never be able to run again. So the fix for this was to make it so that if I'm not running the app, I actually just reject I don't reject the request, I just drop it. And what that does is it moves the responsibility of maintaining the queue of commands that you're trying to send to me to your ship. So if you want me to do something, okay, you store that information. I don't care, right? It's your responsibility. It should be your responsibility. The fact that it had become my responsibility was a big problem, because now it's a security problem, right? That's a DDoS attack, or not even DDoS, just a denial of service. You don't even need to distribute it. It's just one ship. But this shows up in a lot of, in more subtle ways than a lot of other ways, I would say, right? So another thing that we did last year was move the source of truth for which apps are supposed to be running. We moved that into Clay, the file system, which sounds a little weird. It's like, well, wouldn't you want that to be in GAL, right? The kernel module that runs the apps? Wouldn't you want that to be the place that has the sort of ground level understanding of what it's supposed to be running? But actually, because Clay manages kernel updates and manages the build system and manages the file system updates, and it needs to do all of that atomically, Clay has to know which apps are supposed to be running, because if you're not supposed to be running it, then it doesn't try to build it. And if it doesn't if it knows that it doesn't need to build it, then it can actually do the kernel upgrade. Right? So actually Clay needed to know. So moving that responsibility into Clay, now that system works better. Now, arguably, you're hearing like, okay, this is kind of going back and forth and it's not that clear. And so that's because there's asynchronicity. So hey, maybe we should stick Clay and Gall together and get rid of the asynchronicity. And sure enough, we've been thinking about this for a few years, and I bet that by 5 or 10 years from now, we will actually do that. I could be wrong, but I think we probably will. So that's a little subtle, but locating responsibility. But this also applies to the network layer, right? Like, what should a star be responsible for? What should a user be responsible for? What should a moon be responsible for? So it's important. And there's an interesting thing where the responsibility for something often means also the power to do it, right? So with Urbit, I have the responsibility of storing the data for my ship, running my ship. That also gives me the power to do it myself, right? And so because these things tend to align, it's like, yeah, if you want to sort of empower an individual to do something, then they also are going to end up bearing responsibility for it. And these things are going to tend to align. So you want to think about this even at a sort of social layer. All right, the last two are more process related. Second to last one is incrementalism. So what this means is we're not going to jump all the way to the perfect computer. The Arvo kernel is at Kelvin 250 roughly. Standard library is roughly 412 as of a week from now. Speaking in the prophetic future. So we have a couple hundred changes that we can make, a few hundred. All right, so each one of those changes is not going to get us all the way to the end. It's not going to be perfect, and that's okay. It just has to be better than the last one. Right? It just has to be giving us constant progress toward where we need to be going, and it needs to be big enough progress, right? But it's important not to get stuck and think, well, that's not perfect, so we're not going to put it in the kernel. It's like the kernel already isn't perfect. It won't be perfect for a long time. Getting it to be closer to perfect is better than not doing anything. So it's important for us to have that attitude. Now, what's something I didn't mention here that's also important is the opposite of this, which is that sometimes you have to be able to look at a part of the system and say, this sucks. And actually, we should rip it out entirely, or replace it with something that's a totally different design. And we have to have that flexibility. We're not yet at the point where we can say all of the major designs for all of Urbit subsystems are exactly what they will be in perpetuity. We have to be willing to make some hard calls sometimes, make drastic changes if they're needed, and quickly. So we can't yet afford to be dogmatic. Maybe later, but not now. And this is related to the last point, which is we have to listen to users. This is very important. You can go build the perfect system in out in some lab somewhere, and then everyone else just moves on with their lives. Or you build something that's good for one particular use case that you're really thinking about, and then it turns out that's not a big use case, and there are 7 other use cases that are much more important. Or it's the perfect design at some abstract theoretical level, but it's absolutely impossible to use. Nix comes to mind here. No, don't mean to cast shade on Nix. I think they have a very difficult problem to solve. But so I think it's important, and the users for Urbit are actually mostly developers, right? So for the Urbit operating system, like all operating systems, the primary users of that are developers who use the operating system to build applications that run in that OS. Right? So for us, the users are primarily of the kernel space are primarily user space developers, also end users, but it's mostly like we need to be listening to the people in this room. So we're trying to listen, certainly come to us. We try very hard to be responsive to the needs of Urbit companies. All right, so where are we now, right? Like how far have we gotten with this stuff? What's the situation that we're in now? And I would say that the way I'm thinking about this at the moment for core dev is that we want to get to what I'm calling urbit 1.0. This is not a technical version. We're not going to like put it out in the release notes or something. But it's the idea of just what does 1.0 mean in general. It's like, okay, that's the first version that was real, right? That is deployable, production level, industrial software, bulletproof, right? And like, okay, maybe it's not all that fast, and maybe it doesn't have every feature you need, but it's been deployed for real, right? It's no longer an alpha or a beta. It has made it to 1.0. And I don't think we've really gotten there with Urbit. And we need to get there within about a year. We have roughly 1 year to get there. We just have to. So I'll define what I mean by this, and I'll also talk about why we're not there yet and what we need to do to get there. So the rest of this talk is going to be mostly about getting a little bit into the weeds of what specifically are we going to do to fix what specific problems, and where do we expect to be 6 months from now, a year from now. And I'll have a little fun at the end. Not that much fun, but a little. We'll talk about Urbit 2.0. So Urbit 1.0 will fully support social media applications. I say fully to distinguish it from the current condition where I would say, partially support social media applications. Certainly there exist social media applications on Urbit, but do you feel supported? Probably not. So here's what I mean by social media applications. I'm gonna broaden it a little bit from what people usually mean to include some stuff relating to magical internet money, basically. So groups, chats, and DMs. This is like the Talon suite or the Holium suite. So this is something this is the main sort of daily driver of what people do with Urbit right now. But yeah, this has to work. It has to really work, right? Actually, what this means is basically Urbit, the operating system, needs to ensure that any of these apps can have the same feature set as Telegram, or whatever the best in class is at the time. Blogging and microblogging, so Substack, Twitter, right? These use cases have to be supported. Urbit, the operating system, needs to make sure that if you go and write an app that does this, it works, it scales, it's secure, it's reliable, it's performant, etc. Media sharing, Grug won't put movie in Urbit. Grug won't share movie with Chase. Right, so it's a taller ask. It's a taller order than just being able to store media. It also means that I need to be able to share that media with you, and that means that probably we need more network bandwidth than we have right now, right? Like, because that could take a while at current speeds. Serving web apps to the clear web, right? So actually, Urbit should be a viable SaaS platform, right? It's like, okay, you can use LAMP, you can use Ruby on Rails, or you can use Urbit. It's a web server. It should work. It's not that far from it, but this has to work. Actually, Kelvin 4.12 has a couple of features that get us a lot closer to this. The next is DAO management tools, distributed autonomous organizations, or is it decentralized? Kenny and I were debating this earlier. Whatever, decentralized. All right. Well, whatever they are, they have to be able to manage themselves on Herbert. Yeah. Well, okay. So I'm joking a little bit, but this is serious. There are a lot of people running DAOs, and there are a lot of people who would like to run DAOs, but it's not easy to do. And so there are a lot of it's not easy to manage a DAO. People have to cobble together all these different tools and all these different things. They each have their own login. Sometimes they censor you, kick you out, or they don't integrate with each other very well. Different ID systems for each one. So Urbit, this is one of the major sort of general product categories that we've been thinking that Urbit is well suited for over the last year or two, is tools for managing DAOs, because you can have your groups and your chats and your voting app and all these other things, and your document editing and all these other things, all unified under one ID. The applications can interop with each other. It's pretty seamless. You store all the data in one place. You don't have to install lots of different stuff, right? So there's an easy kind of story there, right? So Urbit has to actually work for this. And so this means all the other social app stuff, and then also it has to be able to have reliable connections to blockchains. Right? That's the other sort of big implication. Similarly, crypto wallets, and the big thing that you would want for that is a real security story. Right? Urbit is not secure. Urbit is not secure. You should know this. Sometimes people forget. We do tell people, but it's not. It needs to be, and it will be. But at the moment, it is not. Do not put your keys in there. But you need to be able to put your keys in there. Okay, you don't want to put the keys that you're going to give to your grandchildren in there, right? But whatever you would be comfortable putting in Coinbase, you should be comfortable putting in your Urbit. The last one is actually pretty similar to the serving web apps, but also requires this a security story, which is you need to be able to run web stores from your Urbit. And you need to be able to do monetized software distribution. So you need to be able to manage that from your Urbit. Right, so like what Chase was talking about earlier with vaporware and having an NFT-gated software installation. It's like, okay, well, you want that to be secure, actually. Right? And you want it to be reliable and all the other things I'm about to talk about. But just noting, that's something to keep in mind as a feature that needs to be supported. So there are 4 categories of what's missing, why we're not there. And I will actually go through these, but you'll be asleep, and then I'll talk about how we're going to fix them. Reliability, performance, developer experience, and security. So all these need to improve, and they need to get basically over the hump. I use this phrase a lot. Right? Urbit needs to get over the hump. Each of these needs to get over the hump to a place where it's supporting basically the set of applications that are either actively being built on Urbit or that we expect to be built shortly. So the first is reliability. There are a lot of reliability problems right now. I would say the biggest is that when I try to have a peer-to-peer connection with you, my Urbit tries to send your Urbit a message. Sometimes it flakes out. Sometimes it doesn't get there for an hour. Sometimes it doesn't get there for a month. Absolutely untenable, unacceptable. So Joe gave his talk yesterday about how we're fixing that. But that's something we're fixing right now. There's some error handling problems in the kernel. So if an event that we try, any event that Urbit runs it's like a database transaction or blockchain transaction. It can fail, that's fine. And then the system just rolls back to the previous state. But there are a couple of things that can go wrong after that, where with Urbit, sometimes that event needs to try again repeatedly until it succeeds so that the system can make progress. Or if it fails repeatedly, then the system needs to, because it's running some user space app that was written by someone who uses Hacker News a lot, then the app never recovers from the error, and the system needs to understand that app is now in a bad state, and the system needs to make progress despite it. Right? There are a couple of other things like this, like little details of what the error handling pathways are in different cases, and there are a couple of known flaws there. We need to nail down all of those. Memory limitations are another reliability issue. We usually think of, so you can only store 8 gigs of data in your Urbit. It's actually usually 2 gigs, but you can bump it up to 8. And this means that sometimes as your Urbit is running and it's doing some computation, that computation tries to use more than 8 gigs, and it crashes, right? So that event crashes. I call it this, so this is why it's a reliability problem, not just a sort of storage scalability problem, is that it means that sometimes stuff just doesn't work because we have a limited amount of RAM to play with. So you'll see the bail meme error message, which means you've hit that. Here's a big one, buggy kernel updates. So I know this has been a big problem for a lot of people. Yeah, I apologize about that. That's just something we have to do better on. Our current best idea for how to do this is that before we push out anything, we make sure that all the new code gets exercised and as close to a production environment as possible, ideally as many of them as possible. So every major urbit app company or developer will actually run the code in as close to their production infrastructure as possible before we sign off on it. We also have our own testing checklist that we do ourselves and we encourage other people to run. There's probably more work to do on that subject, but as urbit, in order for urbit to be bulletproof 1.0, kernel updates need to not break it. They need to just work. So that's very important. As I mentioned earlier about the public key infrastructure and jail, learning other people's public keys, that pipeline is fragile. It can flake out. And I think the Vaporware guys are just hitting this with another Ethereum client application, right? Yeah. So, so while jail itself, the vein, I think is probably fine. That pipeline is fragile, so that has to not be fragile. That has to work. It has to be very robust. And finally, there are flaws in suspending and reviving agents. So an agent is an urbit application. It's a program that runs in user space. Gall, the kernel module, runs it. And if you can turn them off and on, sort of like shutting down a Mac app. It's actually a little different because it's a long-running service, right? But it feels like that, like turning off a Mac app, and then you can turn it back on. And if you turn it off and then back on, Gall doesn't maintain all the invariants that it claims to maintain. So if you're waiting on subscription updates, or you're waiting for an acknowledgement for someone else, or you're waiting for a timer to elapse that you had asked the kernel to set for you, those will all get dropped. And then when you wake up, you don't know that you were suspended. So it's very difficult as a user space programmer to correctly handle that, because you don't know that it happened, you don't know what was lost. That information is generally irretrievable. So that's also untenable. We just have to fix that. We have to fix all of these in order for this to be a reliable system, right? And it has to be a reliable system in order to say that this is a piece of real production software that people can build on top of, and they're building companies that this is what they do. So the next one is performance, maybe performance and scaling. And the first item here, and I would say by far the biggest problem with performance at the moment, is the 8 GB limit. Right? This is the big thing that needs to be improved on. If for no other reason than there's a psychological impact of it. Right? If I know that the system can only store 8 GB, then I'm not going to build a file sharing system, even if most people wouldn't actually share 8 GB. But just the knowledge that it would hit the wall, it has a chilling effect. And it's not purely psychological. Also, plenty of people do have way more than 8 GB of data that they want to store. I can't put Llama 2 into my urbit because of this. This is why. As soon as we have a 64-bit interpreter that can handle this kind of data, I can store Llama 2. I can't yet run it. We're working on that. But I can store it. You have to be able to store it before you can run it. Next one is network bandwidth. And I mentioned this earlier, right? So for media sharing, if I have a lot of data, I have to be able to transfer it to you very quickly. So I have to be able to crank up the speed, max out an internet connection. I mean, maybe not max out your 40 gigabit, InfiniBand or whatever, but a typical network connection, max that out. For social applications, right? So for video streaming, video calling, that's probably the highest bandwidth that we really need. But it at least needs to handle that and handle it well. The third one is NOC performance. And I don't put this at the top of the list. NOC is slow, and we're putting a lot of effort into making it go faster. But it has a linear performance improvement on everything in the system, right? Roughly. Right? So something, if you make it twice as fast, then something goes from taking 100 milliseconds to 50 milliseconds. So, right, so you can do twice as much stuff. But other kinds of performance work has superlinear implications. So, especially at the network level, where you might be broadcasting a piece of information to many different people, right? What Joe was talking about is dissemination in his talk. Nevertheless, NOC performance is important, and it does have to get better. So we are working on it. And I would say this is the first time we've really put a concerted organizational effort into NOC performance. the bytecode interpreter was dropped on us by one guy who works part-time. Yeah, Merry Christmas. It's great, but it does not constitute organizational focus. So the last three, load on publishers. Disk, so a publisher on Urbit is somebody who's hosting data that they're publishing to other people, right? So you're hosting a chat, hosting a blog that you're publishing. Maybe you're publishing source code for an app that other people can install by downloading it from your ship. Any of those things, the disk and CPU load on those publishers tends to be quite high. And that can be a scaling bottleneck, right? So there are several thousand ships on the network right now. If you imagine that going up to 40,000 or 400,000 or 4 million, what breaks? This is one of the first things that breaks. Similarly, there's load on relays. So that's the sponsorship hierarchy, stars and galaxies. Tacen hit this really hard earlier this year. And we put a Band-Aid in place, so they're OK now. But we need to actually fix that. Finally, this one's sort of interesting. There's a lack of quiescence. So quiescence means like the state of being quiet, roughly. And with computer systems, it means that the system isn't doing anything. It's idle. It's not in the middle of something. It's not sort of under load. And Urbit never really gets to that state the way it is. It's kind of loud and insistent, especially with the disk, which is particularly bad for native Planet and anyone who wants to use their own hard drive when running Urbit, because it's just pounding the disk over and over and over again. Every time Urbit sends 1 kilobyte of data, pound the disk. Every time it receives 1 kilobyte of data, pound the disk. Every time it was expecting to receive a kilobyte of data and didn't, pound the disk. So it just burns through hard drives like nobody's business. But what that means for native Planet is that their hard drives don't last as long, and then this is a big problem. And that causes all kinds of other problems for hosts as well, because for a host, you really want to be able to take an Urbit and shut it down. And like Tacen can do this, but it's not easy for them to do that well. This kind of goes back to state, actually. Unneeded state and unneeded state changes. You only need to do a disk write if you're changing state. So stop changing the state, alleviate the need for disk writes, get to quiescence. Very roughly. There's a lot of details there. All right, so we've done 2 out of 4. Reliability and performance. The next one is developer experience. Then we'll talk about security. And then we'll talk about what we're actually going to do about this. How many of you have used a Gall subscription? Raise your hand. All right, it's like 3/4 of the room. Did you enjoy that? They're very difficult to use properly. It is probably possible to do it absolutely correctly. It's not entirely clear that it's completely possible to do correctly. And that's just, that's not how we want to be talking about like a major piece of the application model in Urbit, right? Like, it has to be a lot better. Nobody says this about pokes, right? Like the commands, or Urbit, like one app sends a command to another app, like, okay, if you can miss the ACK if you're suspended or if there's a breach, but other than that, pokes work, right? They just work, you just do them. They go through, you get the ACK, you don't think about it. So whatever our subscription system is, and we do need a subscription system, because dissemination is the vast, vast majority of what people do with computers. Whatever that system is, needs to be very easy to use correctly. And it should be relatively easy to use in a performant manner as well. But it especially has to be the case that if I write an app in a weekend, and I slap a few lines of code together and set up some kind of publication, that needs to work. And I don't have to, I can't have to think about it. It has to work without me thinking about it. Okay, so actually, the next line here is scry namespace limitations. And the reason that I call this a problem, even though it's more of like, well, we need more of a solution, is that this is the solution to the Gall watch subscriptions problem, among other things. So right now, Urbit has Urbit, since 2010, has had a scry namespace. And it's basically a URL system where every URL is a permalink, and it starts with the ship that's hosting the data. So if I'm hosting data at rovyns-ricfer /Gall/chat chat/mychatchannel/message33, you can read that from me over the internet using our remote scry network protocol. And that scales well, and it's easy to make correct because it's immutable, right? So it's solid state, going back to those principles from the very beginning. However, there are limitations to what you can do with this right now. So it's only usable for public data, not private encrypted data. You can't just send like, hey, what's your latest? I have to somehow know what your latest revision number is before I can ask that. And there's no way of asking for the next one in a way where I'll get the response quickly. So I can't really use it for live subscriptions. That's really the blocker for using this for chat. So all those limitations mean that we still kind of need Gall subscriptions for now. Right? So we have to get rid of those limitations, kill the Gall subscriptions, and then we'll be in a better state. Package management is missing. Right? So if you're there's just no solution for this. If I'm If I'm writing a Gall agent that I deploy to the network, right, and that Gall agent needs to communicate with several other Gall agents, it needs to import some libraries that other people wrote, it needs to import the sort of header files in Hoon that describe the data structures that I'll use to communicate with them. There's no tooling to help with that. So I'm going to have to manually copy and paste files. Whenever something changes, I'm going to have to manually set that up again. Perhaps I use something involving symlinks. But it's very annoying. It hurts our claim that you don't have to do DevOps with Urbit. And you still don't have to do as much DevOps with Urbit, but you still have to do that, and that should be much easier. So it's unclear if that should actually be something like a kernel feature or even something that just lives in Unix. Hard to say, but certainly it's a problem for developer experience. And the second to last one that's technical is breach handling. So if I breach, right, and then there's code that's running. Oh, sorry, I skipped agent backups, which is related. So agent backups is a really big one, and Native Planet actually has a UIP upcoming for how to do at least part of this. But in general, what users want is that they're running their Urbit, and they periodically take a backup. The backup does get a little stale, but if they lose their actual Urbit, they want to be able to restore from the backup and have some kind of reasonable functionality. And so they want all their apps to understand that they need to be able to load from a backup. Right? And that has to be as seamless as possible and has to lose as little data as possible and get back into a consistent state. So we don't handle this situation very well right now. So there's a UIP coming for making this at least possible. It'll be sort of opt-in on an agent-to-agent basis. But actually, the application model itself is not very good for handling this sort of thing. So that's something we're keeping in mind. Similarly for breach handling, if I breach, right, or if someone else breaches, it's not clear that we actually handle that with full consistency. The last one is just quality of life issues. Because developer experience, yeah, there are these big ticket items, but a lot of it comes down to like lots of little things. And a lot of those little things could be a lot better. The Hoon pretty printer is notorious, my favorite thing to pick on here. But there are lots of little things, lots of little queries that you should be able to do to Clay and Gall, right? Lots of warnings. What? Compiler warnings. Compiler warnings. And errors. And errors, yeah. Yeah, much better compiler errors, dojo errors, right? Why didn't your generator work? Who knows? An IDE?
LSP for Hoon finished.
LSP for, yeah, right, lots of stuff like that. Editor, generally backing up, editor integration, right? All right, so the last category, security. I'll go through these a little quicker. So the first one is front-end sandboxing, which means that when you actually use an Urbit app, you use it from the browser, almost always. However, the way it works right now, that browser code can just access everything on your Urbit. It can send commands to all the different applications. There's nothing stopping it. So we can't have user space permissions, which means that the kernel protects itself from apps, and apps are protected from each other. And with this sort of like glaring hole in that whole system. It just doesn't really help him. It would be the Maginot line of Herbert. Somebody told me this yesterday. I stole the joke. I can't remember who it was from. Neil, thank you. So we need front-end sandboxing. There's a way to do this. And then once we have that, then we can build user space permissions. That's actually mostly built, but it needs to be kind of, there are 2 or 3 loose ends that need to be finished there. And then we also need to protect the urbit machine, we need to protect the rest of your machine from urbit in case urbit gets hijacked, right? So that's sort of security going the other direction. The big way to do this is to drop the permissions of the Unix processes that are running. Very standard Unix thing. Probably not very hard. If any of you are interested in doing this, just try it. There are a whole slew of denial of service mitigations where somebody tries a denial of service attack, and there's a way that we can fight against that. The big one that we're probably going to hit over the next year for Urbit 1.0, there's a long tail there. We're not going to hit all of them, but we'll probably hit one which is what we call, or what's typically called the fail to ban strategy, where it's like if I'm getting a lot of requests from some IP address and port, and then those requests keep failing, then rate limit that IP address, right? Just stop listening to them for a while, or listen much less. All right, so it's a very kind of simple heuristic, but that gives you some basic protections against DDoS attacks. So the next ones have to do with the runtime security. Right, so Urbit has its virtual machine written in C that runs knock. Like all large programs written in C, you have to check it really carefully. And actually, the next version of it is written in Rust, but hey, it's written in unsafe Rust, so you're still going to have to check it really carefully. Maybe a little bit less carefully. But so there's fuzz testing, where it's like, all right, we're just going to spin up, or maybe we'll ask some security firm to do this, to say, okay, just spew garbage into the UDP port and see if you can take down a ship, right? See if you can get it to crash, right? Spew garbage at the HTTP port and see if you can get it to crash. Maybe spew things that look a little bit less like garbage and see what you can do. But this is fuzz testing, right? You're just probabilistically searching for security failures. We do need to do the same thing with jet memory integrity, right? So the jets are these functions written in C that re-implement the same functionality as some knock function, but faster, so that the interpreter can use that instead. And so all of those are part of the security attack surface. And so all of those need to be fuzz tested to make sure that they all handle memory correctly and can't be exploited. And then the last one, which I don't think we'll get to in a year, is formal verification of between the knock and the C code. So that's a mathematical proof, which you could do by hand, but mathematical proof that the logic of one of those functions is exactly the same as the logic of the other function. So there is a way to do this, but that'll probably happen a little later. Okay, we made it to the problem, through the problems. So there are just 2 slides of what we're going to do, this year and next year. And then I'll get to Urbit 2.0 as a little treat for making it this far through the presentation. So the big project that we're doing right now, probably the largest effort, is Aries. Aries is a clean slate rewrite of the knock interpreter, led by Edward Amsden, who works at Zorp. It's a cross-organizational effort from Zorp, Talon, and Urbit Foundation. And this is a large effort with several people working on it. So this is a 64-bit interpreter with what's called a persistent memory arena that can manage up to, I believe, 16 terabytes of data in the last design. And it has a novel optimization technique for knock. So it should manage terabytes of data and also have, we'll see how much faster it is. We're all expecting in the range of 10 to 100 times faster than what we have current. Maybe not immediately, it might take some tweaking, but it'll get there. It's also more amenable to parallelism, multi-threading, yeah, we're all excited about it. So we're working on that this year, but we don't expect it to launch until January or February of next year. And then by February, we expect it to be we expect it to be the case that over 50% of urbit nodes, urbit ships, are running Aries. So it's aggressive. This is an aggressive timeline, and we're going to be putting a lot of focus into this project. The next two are what Joe talked about yesterday. AIMS informal sponsor pinging, and AIMS and FINE unification, which has the the name directed routing is the name of the UIP. It's actually a much bigger change than that. That sort of undersells what it's doing. But so that's these are going to rectify the scaling problem with relays, and also the reliability issues with connectivity. It's a much simpler model for networking and for routing, and so we expect this to just crush the bugs that we've been experiencing, and make it so that it's much easier to analyze, much easier to debug, and we're just going to debug it, get it out the door, and it's just going to work. Right, Joe? Then we just heard a talk earlier on the next one about VER, persistent knock memoization caches. So Matt Levan has built those. Those are just about done, and we're going to make one or two uses of them. And this is like low-level work that makes a lot of other things above it easier to work on, because we can strip out a lot of state from different parts of the kernel. And it gives us opportunities for doing network protocol optimization that we wouldn't have otherwise. So not much is going to come directly from just that step. It's in the steps right after it that are going to help a lot. Breadth-first move ordering in Arvo. This is a way of dealing with some asynchronicity, I would say, right? So when, and this is another sort of relatively low-level feature. This is the one thing we're changing about Arvo. Remember earlier, it was like there's just one thing, and hopefully this is not like Lord Kelvin in 1890 saying there are only two problems with physics, one of which led to quantum mechanics, and the other one led to relativity, right? So, so there's just one problem with Arvo, yeah. So the way Arvo handles effects between kernel modules is if one kernel module emits two effects, then it takes that first effect and it delivers that to the kernel module and runs all the ones that come after that, and then traces that whole tree. So what we call depth-first move ordering, because it goes all the way down the tree of possible effects from that. And only once that whole thing is finished, then it runs the second effect that the first thing ran. So we're depth-first traversing everything that comes after the first move, and then depth-first traversing everything that comes after the second move. And then there's a certain elegance to this, but in practice you end up with a lot of weird stuff, because that first move can trigger other things, and then you lose the chronological ordering of the effects. So you can end up with moves coming in out of order a lot, like in reverse order from the way they were emitted, and it's very difficult to reason about this. Your mind kind of like twists around a corner. At least mine does whenever I encounter this. So breadth-first move ordering is the opposite. Arvo runs, there are these two moves that come out of one vein. If there are two other veins, it runs both of them logically in parallel. So there are no data dependencies between them. They're logically simultaneous. This introduces a new concept of synchronization within the kernel that wasn't there before, which also enables us to pin the scry handler and establish full referential transparency for that. And also we could run it in parallel if we had a parallel runtime. It's probably not that big of a deal, but it would be nice. Generally, a lot more sanity, a lot easier to reason about. So we're doing that this year. It's going to happen. We're also working on scry over HTTP, right? So that scry namespace where you have this permalink, it starts with your ship, and you can request data at that. Right now, it's only urbits that can read that from each other, but there's no way to read it over the web from a browser. So we're exposing that. We're going to make that so that doesn't do a disk write, recurring theme. And, but that'll be very nice. You can use download files into the browser, load files. It'll do file type conversions. There's a UIP for it. There's a nice full spec for exactly how it works. So feel free to check that out. And finally, encrypted remote scry. So earlier I said there are limitations with the scry namespace and the way you can use it. One of the big limitations is that there's no way of publishing data to like only a small set of people and maintaining the privacy there. So by encrypting the path and encrypting the data at the path, we can still use that scalable dissemination network protocol, and still use the scry namespace for its solid state programming benefits, but actually have that go over the network and have that work, and have it be private. So those are the big ticket items for this year that we plan on deploying by the end of the year. Then I'll also talk about the first half of next year. All right, so by the end of the first half of next year, we expect the Urbit to be at 1.0. That's right, Matt. So the order of operations here, the exact set of projects, gets a little murkier because it's a little further out. And there's a good chance that by the time we hit the beginning of next year, we'll have better ideas. This happens a lot. So I'm not committing to this exact sequence of projects here, but this is roughly the shape of what we're going to be working on mostly, and there will also be a lot of other little things that come in. But here's the general set. So Aries production deployment, January, February, getting out the door. It may not be much faster than current system. It may even be slightly slower, but it'll be able to handle the 64 bits of data storage, and it should be stable. So the next one is called Pine, or as Josh Lehman pronounces it, Pinay, to rhyme with Finet. So what this is a network request for the latest value in the namespace. Earlier I said you can't do that. I can't just be like, hey, what's the latest value? What's the last chat message you've heard? Can you send me your last chat message? You can do this with HTTP. You do it all the time, right? And you just can't do it with Urbit. It sucks. And we need to be able to do that. And we need to be able to use scalable dissemination through the scry namespace with solid state. You know what I'm going to say now. So Pine is something we're going to build that next year. That's part of the solid state subscription story. We have to have that. And that's actually something that will just improve the developer experience in quite a few ways, because things like Docker and Treaty, Docket and Treaty, Freudian slip, are like a lot of those apps actually probably shouldn't exist, and those should just be queries that you can ask Clay or Gall in the kernel, but you have to be able to ask them with a Pine. So this is another thing that should just reduce the size of the code base, strip out a couple of extra layers in a few places. Gall step nomadism is the next. So Philip wrote an excellent essay about step nomadism in contrast to step wisdom. This is how we're going to fix agent suspension and in general fix a lot of the application programming model in Urbit. And so this has to do with making state explicit, making all pending input and output tracked by the kernel and available to the application, and available to a later agent that was pulled out from backup, right? That was restored from a backup. The backup should include all pending input and output, so that when that backup gets injected into the next version of the ship after a breach, that next version of the ship can tell what the previous version was in the middle of doing. This may eventually lead into what we call a shrubbery, which is basically that same idea but laid out as paths, values at paths in the namespace. Maybe, maybe not, but it's certainly a lot closer. But it's a big change to the application model. You'll end up thinking about your Gall agents in a significantly different way. But we have to get this done by a year from now. Like a lot of these kinds of changes, it's probably not very much code in the kernel to change it. It's just a big difference in how we think about it. The other one is Gall desk-based agent namespacing. How many of you know that if I install app foo and app bar and try to install app bar, then if app foo has an agent inside of it called debug, and app bar also has an agent inside of it called debug, that I will only ever be able to install one of those two things. Rage-driven development. So the solution to this is that when I as an agent send a command to another agent, instead of just saying, okay, it's this ship and this agent name, I'll say it's this ship and this desk and this agent name, and that way they're namespace. This is what namespaces are for. In fact, I think that should be a path, but we can fight about that later. All right, and the last big ticket item has a couple of components, but it's user space permissions. So this is a system that's sort of like your iPhone permissioning system, right? Where it's like, this app wants to use the camera. Do you want to let it? Right? Somewhere between that and like an OAuth system, like login with Google, is like this app wants to see your contacts, and right? It wants to send messages to your friends, right? So we have to have a system that's somewhere in between those, and then the kernel needs to enforce that. Right, so there's a user space component that actually shows you these modal dialogues and does redirects on the front end and all this fun stuff. And then on the back end, we actually just have to enforce the rules. And there are a couple of difficult pieces here. So front end sandboxing has to happen. I talked about that earlier, but that's the browser-based security check. That has to happen first, so that it's sort of real and complete, doesn't have a big hole in it. And second is that the first version of this didn't really handle kernel updates properly. And it's actually a difficult, thorny problem. So we probably need something like, well, I'm proposing we use this system called Ulam, which is this little JSON-like language to describe those data structures, describing the permissions, so that an old kernel can read the permissions that an app wants from a new kernel without having to upgrade into the new kernel first. So you need a data language that the old kernel can read and interpret and display something reasonable to the user. We have to do that somehow. So we need those two things, and then the actual user space permissions where it can be deployed. The way I see this is probably going to be like an organizational effort that comes after the Aries deployment. So we're going to deploy Aries, then put out the next fires for a month, and then hopefully they're not that bad, but there's going to be something. And then we'll switch to, as an organization at UF, focusing mostly on user space permissions because it's pretty big. And then we'll get there. So that'll get us to Urbit 1.0. And after that, you can, writing an app on Urbit should feel like writing an app on Linux, right? Where like you write the app and there's some bug. You don't think, oh, like it's a Linux bug. It's like almost certainly not a Linux bug, right? Like, we have to get to that point, right? It's like, oh, there's something that doesn't work. Like, okay, probably the app dev messes up. We can't say that right now. Okay, so that's Urbit 1.0. What's Urbit 2.0? Right? We don't talk enough about this, I think. We're like, where are we going? Right? And like, what are some things that you can do? What are some things that the system can do? What does Urbit, the system, even look like 10 years from now, 20 years from now, 30 years from now? So here are a few things. One clear one is you got to be able to stream video into and out of your Urbit. You got to be able to store, train, and run your own machine learning. This is like import Llama 2, tweak the weights with your friends or on your own, based on your own data. Right? You see Portal is already doing this, but they can't do it inside of Urbit yet. Right? So collaborative training of AI systems, machine learning. I got into Urbit in 2016, 2017 because I was interested in doing large-scale distributed computations on it. I still think that I still want to do that, and Urbit should be able to do that. Internet of Things support, Native Planet's starting to work on this, but this is why we have moons. We have moons. Every time you when you buy a planet, you buy 4 billion addresses. It's kind of a lot, right? Like, what are you going to do with 4 billion addresses? It's like, well, you could run an oil pipeline and all the sensors in it. Your Urbit will turn into your personal CDN. This one we're actually not that far from. And as for the LLMs, if we have data storage and we get some jets on the already existent neural network code in Hoon, then yeah, you can go ahead and run LLM. So that's also not that far off. Disputations about floating point non-determinism notwithstanding. We're just going to have to figure it out. But yeah, so a personal CDN, we talk about this a lot with Remote Scry, right? And this general idea of like, okay, my ship, I'm running it on my laptop, but what if I make a post that goes viral and millions of people are trying to read it? What you need there is you need a data center in the cloud, right, that handles those requests. A star should actually be a data center in the cloud. And so my star, my sponsoring star, should actually be able to field those requests for me. And so then it just, it's in, let's say, AWS. And when it starts getting lots of requests, it spawns a bunch more horizontally scaled Scry cache servers. The Scry cache is embarrassingly parallel. It's very easy to scale horizontally. So there's this idea that peer-to-peer systems can never scale. And I just don't think that's true in Urbit. And I think what they really mean is, Kademlia doesn't scale, distributed hash tables don't scale, and blockchains don't scale. And Urbit is none of those things. So the next one is async parallelism for the main event loop. What this means is that instead of, let's say I download some source code for an app, and then I want to compile it, and the compiler, let's say, is still slow, then I shouldn't do that as one item that blocks everything else I can do with my Urbit and locks up the main event loop. We need to do what Node.js programmers have been doing for 12 years, which is you kick it out of the main loop. All right, so you have a long-running process, you kick it out of the main loop, it finishes asynchronously, you inject the result back in. Totally doable. Joe has a very clever design for how to make this not use a ton of disk writes. Parallelism should be a lot easier with Aries, so we might actually just go ahead and build this sometime soon. What that enables is that you have fast twitch response from your Urbit no matter what it's doing, even if it's compiling 10 things and running an LLM and whatever. That's all happening asynchronously, you don't have to worry about it. Run WebAssembly in Nock. You want to write your code in Rust, compile it to WASM, and run it inside of Herbert, you should just be able to do that. We have a grant out for this. Actually, I don't know if the solicitation is out yet, but we at least have a proposal out, and the solicitation will be out soon if it's not already. But yeah, you should just be able to do it. No reason not to. Similarly, I want us to add a scripting language. Hoon, as I mentioned earlier, is a systems programming language, which means it's statically typed, low-level, concrete, compiled, right, as opposed to interpreted. There are lots of scripting languages out there. They're really useful. The further up you get up the stack you go, the more useful there are. Right? Nobody's going around writing, little scripts in C++. Right? No, you write your script in Python. You write your script in something, Ruby, Lua, something like this. Right? That's what they're for, little glue languages. So we need a little glue language in Urbit, and I think that it should be as different from Hoon as possible. Well, we should have a couple of them, actually, but one of them should just be the most normie of normie languages. I actually think that we could implement Lua, the exact Lua spec in Urbit, and give it imperative access to the kernel, so you'd have what feels exactly like a Linux-style syscall interface. For example, we should have that. We should have something that has algol syntax like JavaScript or C, right? We should have a bunch of these, actually. Real-time graphics. I think this is actually doable at a certain point. The way it would work is every 10 milliseconds, so 100 times a second, scry in parallel, a computation out of your Urbit that you can use to construct a frame. And that gets jetted with a bunch of code that interacts with the GPU. You could jet the whole top-level thing if you wanted to. I don't think that's as far away as people seem to think it is. Now, I don't know about really maxing out the machine. Probably won't get there, but you could do some stuff. Similarly, Urbit native UI, right, would extend, nouns and the Urbit programming methodology out to the clients, right? So you'll still have, a runner, renderer type thing in iOS and in the browser and in GTK or whatever. But you could ideally write that once in Urbit, and maybe it still has some limits on its use cases, but it's not clear to me that the DOM model of the web page is really what's going to last for the next 100, 200 years. I don't think it will. I certainly don't want it to. Knock chips, knock processors. There will be an FPGA roughly a year from now. It takes more money to build an ASIC, an application-specific integrated circuit. It takes even more money than that to build something that's a whole general-purpose processor. But at a certain point, it becomes worth it, right? And you can analyze what that inflection point is by looking at crypto, right? When did they build the ASICs? There's a point at which it happens. And when do they start building ASICs for machine learning? There's an inflection point there. Right? When do they start building ASICs for TCP? Because TCP is actually done mostly in hardware in high-performance machines. So you could do that with AIMS as well. So it's actually not just a NOC processor that's interesting. NOC processor is very interesting, but then the next thing is an Arvo processor, where you take a relatively frozen version of the Arvo kernel and you tape it out as a circuit. You can't really do this with Linux, but you can do it with Arvo. Very reasonable. And you could even do it with other chunks of the system. And then you could even extend this further, and you could say you have an urbit machine. So there's a motherboard, so there's a CPU and the motherboard. And all that the motherboard implements is the urbit I/O channels. Right? Ames, Bane, Clay, Dill, Air, Iris, Con, Lick. But just those. That's it. Right? So you could have then a whole machine. Right? And it's actually very useful as a communicator. Right? But that whole machine, all it could do is run urbits. And so that you could actually, because urbit's doing one thing, you can have it do that one thing really well as a piece of hardware. That kind of constraint that goes all up and down the stack that urbit provides, that sort of full stack, vertically integrated constraint could enable hardware that's quite a bit more efficient, cheaper, more secure, certainly more secure. Similarly, transport agnostic networking. I need to be able to mail you a USB drive, you stick it into your urbit, and your urbit interprets that as a bunch of messages. It takes the ACKs, the acknowledgements, and writes them back into the drive. You mail it back to me, I plug it into my urbit, it does the acknowledgement. That should just work. Similarly, this should be able to go over mix nets, Tor, I2P. You should be able to put messages on chain, have somebody else read it off the chain. No reason you can't do this, especially with the networking system that we're building right now. And once we've done all of these things, then of course, we'll make anime real. And so I'm very excited for where this is going. I think we've seen a lot more progress in the last year towards some of these more like bombastic goals than I would have expected. So I'm going to end with a sort of call to action here. Ask not what your operating system can do for you. Ask what you can do for your operating system. And what you can do is you can go to the Urbit Improvement Proposals, the WIPs, and read through them, comment on them. Say what it is that you like, what it is that you don't like. Make issues to say what you would like to see a proposal for. Write your own proposal. And there's a good chance you can get grant funding from the UF to actually implement it. And we'll certainly talk to you about it. So this is rapidly becoming the center for core development, is this repo. So certainly check it out. There's a nice little listing of the 13 UIPs and what to do at the beginning. Some nice little pros. And we're going to be putting a lot of effort into this system. This is the main way that we're going to be communicating about what it is that we're doing, what we're about to do, what it is that we're considering or that we have considered and decided not to do, and why not. So please take a look at UIPs, read through them, write some of your own. Thank you.
Do you have any? Hello? Oh, perfect.
I have two related questions. The first is, why do you say we must do this in a year? Where does that must a year come from?
It's about how much money we have.
Oh.
No, it's more than that, actually. It's about how much money we have, and it's also roughly the timeline that the Urbit app companies need, I would say.
That the Urbit app companies need?
Yeah, like you work at an Urbit app company.
And the other question is, what in that sort of long grab bag of things, what frightens you the most about fitting in that year? Is there anything that jumps out?
That's a good question. I think it's the Gall agent suspension, because we don't have a spec for that yet. Most of these other things we either have a spec or we're very close to having a spec, but for that it's like we have an idea. We have a general sort of architectural philosophy, but that's like 2 or 3 steps from a spec.
Cool, thanks.
I also have 2 questions, one of which is related and one of which is sort of less so. We have this notion of Kelvin versioning where the version number counts down until it reaches 0 and then the software is considered finished. I noticed that you presented the idea of urbit 1.0 and its successor being urbit 2.0. What significance does this have, and is Kelvin versioning like the wrong way to think about urbit as an entire system, and we only version its like subcomponents, or like what is the reason behind that?
Okay, yeah, so I guess I wasn't that clear about it. So I like to think of urbit as primarily a specification. All right, so it's a specification for machine code, language, operating system, network protocol, and an application programming environment for user space apps, right? All that is a spec. So that spec is subject to Kelvin versioning, because what we're trying to do is freeze the spec to a place where it can be frozen forever. Right? As the first quote described, or alluded to at least, this has happened to a lot of other things in software, right? If you look at JSON, there's not going to be a JSON 2.0. Not going to happen. Right? And this is true of a number of other things too, right? You can find a bunch of stuff where like, yeah, it ain't changing. But nobody's tried to do this for a whole operating system or a whole sort of machine or like a whole model of computation, not in any kind of concerted manner. I think Urbit is the first project to really try to standardize something in this particular way, right? So we're trying to say, okay, what is the part of computation that can be factored out and say, okay, we're going to freeze this part of it, and everything else will change around it, but this will be this island of stability that will just be there in perpetuity. So Kelvin versioning, in my opinion, is a very good way of trying to manage a project that's trying to get there. So the way I think of it is actually not necessarily that something gets exactly to Kelvin 0, and therefore it is frozen, and until it gets to Kelvin 0, it is not frozen. And a good example of this is knock, right? Like, knock is at version 4, we could change it a few more times, but we probably won't. The number tells you something, right? But it's a bit of a heuristic. The number tells you roughly how far you have to go, right? It tells you something like, okay, if you build an ASIC for knock, you only ever have to build 4 more, right? Because there will only ever be 4 more changes. But it also tells you, like, yeah, maybe it doesn't get that far. And different layers of the stack may kind of peter out and kind of end up resting. Maybe Hoon ends up at version 100 and never really goes past that. I actually think the further down they go, the better. And a lot of people have Kelvin anxiety, and they hear like, oh, you only have 250 changes to make. Like, aren't you worried? It's like, no, I'm worried we have too many. I'm worried the numbers are too high, actually. Because then there's a little bit less of a signal that they give psychologically about, well, how much can people rely on it not changing? I think it'll be fine. I think we'll work it out. But the Kelvin versioning is an attempt to sort of lean into and recognize the fact that this kind of software will actually get standardized, de facto standardized, just by the market. So that's the spec, right? So the spec applies to kernel space. It doesn't apply to user space. There may be parts of user space that people want a Kelvin version. I can see that being useful for certain things. But everything underneath Urbit, everything in the runtime, that's the part that needs to vary continuously, right? So you don't want to Kelvin version that, because somebody's always building a new piece of hardware. Somebody's always building, coming up with a new clever data structure for representing something, or right? Like, you can always optimize the implementation. So there's a separation of mechanism and policy here, right? The policy is that which is Kelvin versioned, that's in the spec for kernel space. And then the mechanism is whatever var is, right? Or whatever Aries is, or whatever that future chip is, that's or the future device that's a pure Urbit implementation. So urbit 1.0, urbit 2.0, I'm just using that very I'm waving my hands, you know what I'm saying? I'm using it to conjure up the image of like, you know, it's production level. It's no longer an alpha or a beta, but it's not an official designation.
Okay, thanks. And my second question, which is basically unrelated to what you talked about, but I'm still curious, because you mentioned Rust a few times. I'm curious if you've had a look at Zig at all, and if you have any opinions on it.
Zig seems really cool. You'll have to ask Joe.
Okay.
Sorry, Joe. Resident Zig expert.
There's been a variety of talks this week that have touched on composability and databases, gripes about Clay, liking it, whatever. Where do you see that kind of in this stack in terms of, you know, ripping something out, putting something new in, having it happen in user space?
Yeah, so I think probably most if not all database systems in Urbit should live in user space. The one exception I could think of to that would be if you want the kernel space to guarantee referential integrity for you across applications. That's, I think, the only reason that you would want any kind of database in kernel space. Because otherwise, it's up to the applications to sort of play nicely with each other and collaborate to ensure referential integrity across them. More or less. I mean, maybe there's some tricks that you could do in user space to ensure that, even without the kernel. But yeah, I don't know if that's I don't know if that'll ever be enough of a factor to try to push it into kernel space. And if we did, then, you know, the problem is that there are a lot of different database models, right? So you know, there's the relational algebra that Jack is implementing. Was it Dodd? Who's the guy's name? Yeah. Yeah, Dodd's relational. COD's relational algebra, right? Which is like, you know, a fairly complete. My understanding is a, you know, kind of complete mathematical system. Then there's, you know, the thing that SQL implements, which is close to that, but not exactly that. There are categorical databases, there are EAVT databases, there are graph databases, right? So like, you know, which one of those is fundamental that you could imagine putting in the kernel and Kelvin versioning? Are any of those fundamental enough? And my general hunch here is that none of them are fundamental enough, and that there's going to be a layer underneath the database that does live in kernel space that has to do with the scry namespace, right? And I think that each database table is likely to be something that's accessible through the scry namespace, and then, you know, joins on those tables will be sort of compound queries that read from multiple scry paths. And I imagine that we've talked about a number of different indexing schemes there, some of which involve sort of high-level query language like SQL, and some of which don't. So I think the database story in Urbit is yet to be really fleshed out. I'm happy that there are now 2 or 3 different versions of databases being built, right? So there's JAX, URQL. The Holium guys have Bedrock. There's another one from Ukbar. And what was it called? I think it's called Nectar, I think. Nectar, yeah. So there are now like a few different sort of takes on databases. And I hope there are more. And I also think that we should do more of sort of standardized data layout, probably for, I don't know, I'm not entirely sure, but there's a vague idea that comes up a lot, and has been coming up a lot for a long time, which is basically like a trie with ordered values. So GraphStore was actually an instance of this, where it was a trie data structure where, you know, with ordered values. So you have a sort of a recursive folder structure where you can do efficient range queries within that. And I think it's likely that Clay should probably use a data structure like this. Maybe the case that application data by default should use a structure like this, or use something that can easily be translated into and out of that. Maybe it's too constraining, but that's a sort of alternative way of thinking about data layout in Urbit that feels like it would lean in to the tree a little bit more, right? It's like a very natural kind of tree-based system in a way where you know, SQL systems or EAVT systems like Datomic would be sort of mapping a different kind of logic, like a more constraint-based logic, I think, onto the tree, which might be the way to go. But I suspect that it'll end up eventually living on top of a lower layer that's more directly tree-oriented. I don't know, though. Yeah, okay, I love this question. So yeah, Urbit 3.0 runs in your neural interface. Yeah, and it's stored, its event log is replicated in a decentralized storage system. Yeah, it has all kinds of crazy multi-threading that we haven't even thought of. And the what else is Urbit 3.0? Who else has ideas for Urbit 3.0? Not crystals. Let's not get ahead of ourselves.
Network spirituality.
There you go.
So Aries is like two major parts, right? The 64-bit part that gets lots more storage for Urbit, but then also the novel approach to knock interpretation based on what used to be subject knowledge analysis, but is now what, SAC, subject. Is it? Oh, they didn't do that?
That's close enough. What's the rest of the
Anyways, what's the status on that? Because that's sort of the
on the subject knowledge analysis?
the more difficult part of the Aries.
Well, you'd have to ask either Edward or Logan, but my understanding is it's going quite well. Mm-hmm. Joe, do you know the latest status on it?
My understanding is it's complete. It's not proven in production. It's not proven at scale, but it's done.
Yeah, that's my understanding as well. Yeah, it's nice because that really is like probably the most risky of the three parts of that project.
What was the third?
Well, I like to think of that there's the persistent memory arena, right? The PMA, and that's what stores all the data, right? So that's what stores your Arvo snapshot, basically. I think, and your working state. But then there's also the knock interpreter. Instead of having the loom and the road system, it has two stacks that grow toward each other, right? And so there's also that stack-based interpreter there, right? Or that's like the allocation, the noun allocation for the stack-based interpreter. I guess it's not just nouns. It's like, yeah. But anyway, yeah. There's the state of the execution, right? And there's the whole interpreter that knows how to use that. And then there's the third one is the optimization, yeah, which is the static analysis step. Yeah.
So in terms of eliminating asynchronicity, what about GAL-managed request response? Or are threads already managed by GAL? I'm not clear on that.
Threads are sort of managed by GAL. In the very long list at the beginning of things that don't feel good about Urbit, it's one of them was how threads are implemented, because they were implemented in user space first as a way to not sort of mess with the kernel and be able to experiment with them. But then they were made officially part of the kernel through the con vein, so that external processes could use a request response protocol with Urbit, stateful request response. Because the thought was that's easier to integrate into a bash script, basically. And so then that external system can call into con the vein, and then con runs those threads. And these are spider threads. They're not like operating system threads normally. I think we should rename them, actually, because they don't have anything to do with parallelism. It's really like a monadic input-output sequence. But it's like a script. And then, so that's a thread. But then the way that con actually executes a thread is that it asks GAL to run the spider agent, which is in user space. And then that runs it, and it sort of goes up and around. And it works. But I think that we're better off moving threads into the kernel at this point. I think that's going to be easier to enforce permissioning. And then once we have them in the kernel, then yeah, maybe that could be an official API for your application, is that you could expose some threads that other apps could call. That's a bit of a vague idea, but yeah, I don't know. I think there's something in there probably.
Yeah, so let's say you have a thought,
right? Like something that
couldn't be me.
Yeah, right. Something that like maybe should be in kernel, but maybe shouldn't. But either way, like, or even is planned for core within like the next year and a half or so. But you don't want to necessarily enforce your opinion about this thing on other people, but you still want to experiment with this thing that could be useful in the kernel or core, later on. What kind of like thought process do you suggest people take to like think about like experimenting versus like working or kind of coordinating with core?
Yeah, it's a great question. So if someone who isn't you wants to do this, I was hearing that whole thing like an Arrowhead trip report. But yeah, no, it's a very good question. So I think I would say it depends on what you're trying to do. The first thing to do is come talk to us, and we can try to answer it on a case-by-case basis. But generally, it's usually better to experiment with things in user space. You can do a lot in user space, right? But it also can be very useful to experiment in kernel space. It's really easy to write a vane. People don't know this really, but like just to write a sort of blank vane. What, isn't it?
This is what core devs don't want you to know.
Yeah. One weird trick for improving the kernel is that, you can just write your own vane, and it's actually quite easy. And then, yes, you can experiment with that really easily. So that's much easier than modifying an existing vane, I will say that. That's tough, especially if the vane is Gall. But you can always write a new one called Schmall and run it right next to it.
If you see Schmall anytime soon, I don't know who wrote it.
Yeah, I don't either.
Any other questions?
I think I was subtly called out as grug during the presentation.
No, we're all grug.
Okay, great. I'm gonna wear the grug hat for now at least. Okay. Here's my grug statement, and then I want you to convince me that Urbit 1.0 is actually going to get us there.
Okay.
I upload 10 movies to my Urbit. Say they're 100 megabytes. I add 10 ships to some permissionless to download those movies. Those other ships, as soon as they get added, start downloading the videos automatically, and then those users from whatever edge device they have can watch the videos, like very basic social media application. So step one, I upload 10 movies to my Urbit. What was
the last step there?
The last step is they've got these videos on their ship, and now they can watch the videos.
Yeah.
Yeah. So step one, I can upload 10 videos to my Urbit. What is like 1.0 doing to get us there for like that step?
Yeah. Okay, so you need a few things.
Yeah.
So you need arrays, so that you can have 64 bits, you can store the videos. As for the actual upload, well, you could do it in Clay. It's not particularly nice to do at the moment, but you could. Or you could use a web upload form, and that should work as well as any web uploader works for large files. Which is to say usually not very well, unfortunately. But if you have a good network connection, it'll be okay. And this is sort of a general problem. So that's, I think, what you need to get them in to your Urbit. In order to expose them
if I fail, if I shut my computer down and there's a half uploaded video sitting in my new Aries loom, like, is that on the...
That wouldn't happen over HTTP. It'll either get the whole thing or not.
Okay.
Yeah. Same with Clay, actually. If you upload it through Clay, it'll either get it or not.
I add 10 ships to the permission list. Like, is that permissioning to read something from Clay in this case then?
So you could do it either through... So you could do this today with Clay if you wanted to. But if you did, then you wouldn't be able to use the remote scry protocol yet. In order to use the remote scry protocol, which is going to be the fastest way to deliver it to 10 people, we're going to need encrypted remote scry, which is scheduled for this year. And then, and I think that actually the way I would do this is, when I load when you load it into your urbit, right? You load these 10 videos into your urbit, and then you go through and you add 10 people, right, who are allowed to see it. When you click that button, your app that's managing this actually sends a poke over AIMS to each of those 10 people saying, hey, here's a set of files at these paths. Go ahead and download them. And then the corresponding app on those other ships will hear the poke, acknowledge it, and then start to download.
Okay, so step 3, they start downloading the video. Let's assume at least some of them aren't directly peered with me already.
Yeah, that's fine.
Okay.
They shouldn't have had to be peered with you. Peer discovery should just work.
How long does it take in Urbit 1.0 for these 10 ships to download these videos from me?
So the good news is it shouldn't take significantly longer than one ship downloading. The bad news is it depends on how fast we get the network bandwidth to go.
And that's slated for 1.0?
Yeah, so some network improvements, like network bandwidth improvements, are slated for 1.0. I don't have a great sense of exactly how far we'll get with that.
What's the, like, if we did this today, let's just pretend we had the storage.
If you did it today,
100 megabyte videos.
Yeah, okay, so what's the current bandwidth max? It's like 200 kilobytes per second? So 5 seconds per megabyte. So 500 seconds for 100 megabytes. So 500 seconds is some number of minutes. 9 minutes. 8 minutes. So yeah, it would take about 8 minutes. And yeah, but the nice thing there is if you can use remote scry, if we have encrypted remote scry, then it'll take 8 minutes and they'll all get it, even though that's the max that one's getting. So yeah, I mean, we want that to be quite a bit faster. And I don't have a great, do you have a? We don't have estimates. Yeah, we don't have estimates, but we should be able to get significantly faster than that. We know what the bottlenecks are roughly. So their bottlenecks are, they can be disk writes. The congestion control algorithm isn't necessarily all that well tuned. And the third one is that there's Arvo processing overhead. So Arvo does an actual event for each packet, so for each kilobyte. And so if we can, and right now for FreeNAND there's authentication overhead from signing every packet, which is ridiculous. So we can get the authentication overhead down to pretty much minimal for large data. Even in this first version, that'll be minimal. Congestion control, we're not going to touch for now, but we might do some incremental tuning of it over the next incoming months. And the big one is going to be figuring out how to basically batch packet delivery some way, so that the Arvo, there's Arvo's outer loop, just like running an Arvo event, is about 2 milliseconds, and so that'll cap you at 500 events per second, right? And so that'll cap you at 500 packets per second, which is then 500 kilobytes per second. So we certainly want to go above that. And so what that means is that you have to batch the packets so that you're delivering, say, 10 or 100 packets into Arvo at a time. And then you only pay that 2 milliseconds for every 100 packets.
Got it. Okay. And then the final step. I've got my video. I've gotten my Grug video, and I want to watch it now.
Yeah.
How does 1.0 get us there? That's like streaming from my Urbit, right? So
yeah.
Do the users then need to like re-download these videos to their devices to actually watch them?
So that's a good question, and we might need to build something to allow a partial file download.
You need registries over HTTP to
yeah.
serve it for streaming video.
Yeah, so that's an interface. So that's yeah, but we would need to build that. So that's I think that's a project in similar level of complexity to Scry over HTTP, which we're doing now. So like roughly a month of from like inception to deployment. Yeah. Does that answer your question? Cool.
Okay, maybe just one more question.
Oh yeah, kind of a small question, but the package signing stuff and kind of like the merging of FNA and like it's like when do you have like a rough timeline for that?
We want it done by assembly and then deployed by the end of the year.
Awesome. Thanks.
Okay, and with that, let's give Ted a round of applause, everybody.